Section 5.4, calorimetry. We're going to begin this section by looking at Table 5.2 from your textbook, which is a list of specific heat values for some common substances. So this is by no means an exhaustive list. It's just a few substances. And these substances are, some of them are elements. For example, aluminum and gold. The symbol for gold is Au. Graphite, which is carbon, a form of carbon. Diamond, which is another form of carbon. Not sure why they picked those materials, but they did. Copper, iron, mercury. Remember, mercury is the one metal that at room temperature is a liquid. And then there's liquid water and liquid ethanol. So those are two compounds. And the specific heat capacities, or specific heat for short, are given those values in the units of joules per gram degree C. And the specific heat capacity, the symbol for it is S for your textbook. Call that the specific heat. And it's used in an equation. Q is equal to S times M times delta T. Sometimes referred to as the calorimetry equation. This equation allows us to calculate the amount of heat transfer for a given substance, for a specific substance, by measuring the mass of the substance and measuring the temperature change of the substance as a process occurs. So imagine it this way. Imagine that we have a block of aluminum. And heat is flowing into the aluminum block. It's a transfer of thermal energy into the aluminum. How would that happen? Well, we could use a heater, or we could use a Bunsen burner, or we could breathe on it with our breath, which is hotter than room temperature. But we're transferring heat to it. Okay. Well, as that heat transfers, heat is Q. What this equation says is that if you measure the change in temperature of the aluminum, and remember, change in temperature is the final temperature minus the initial temperature. So let's say, for example, the aluminum block is at 20 degrees C, room temperature. And then heat is transferred and it goes up to 25 degrees C. That would be a change in temperature of 5 degrees C. Now, if we measure the mass of the aluminum block, and we look up the value of its specific heat, which in this table is 0.900, right? That allows us to calculate how much heat was transferred into the aluminum block. Now, that's a very powerful ability, right? We can actually calculate, we can quantify the amount of heat transfer by using a very simple equation. Okay? Now, there's another equation which is similar to that, and that says that Q is equal to uppercase C times delta T. This also allows us to calculate the heat capacity. The heat transfer to the aluminum block. In this case, the uppercase C is equal to S times M, if it's an aluminum block, for example. The mass times specific heat would be equal to this capital C, and capital C is called the heat capacity. Okay, heat capacity. So it's just equal to the specific heat times the mass. Now, the heat capacity is useful when we have more complicated situations. So for example, suppose instead of having a piece of aluminum that I could weigh, suppose I had a shoe. Well, how about a sock? Actually, you know what? We'll go back. We'll make it a shoe. Suppose we have a shoe. Now, a shoe is not for the most part, a shoe is not one type of substance. It's not made out of one particular material. It's usually made out of a mixture of materials. So the specific heat capacity, or specific heat S, is used when the substance is pure, when you have one type of substance. So it could be aluminum or water. When you have complex mixtures of things, then it's not that practical. So, because each part of the shoe might have a different specific heat. So in that sense, what you do is you use the heat capacity. So what we would do is we would say that the heat transferred into the shoe, maybe you put your foot in it and it transfers heat to the shoe and the shoe warms up. Well, that would be equal to the heat capacity of the shoe times the change in temperature. Oops, sorry, that's a delta, not an A. Delta T. Okay, so you might ask, well, how do you know the heat capacity of a shoe? You'd have to figure it out some way. What you'd have to do is you'd have to transfer a known amount of heat, Q, measure the change in temperature, delta T, and then that would give you the heat capacity of the shoe. But so heat capacity, it can be used with the aluminum block because capital C is equal to S times M, but it's more commonly used for complex substances, which are mixtures of different materials. Okay, so those are the heat capacity, heat calorimetry equations that we often use. Now, a little bit about water. Water has a specific heat of 4.184. You'll look at that, it's over on the right side. So the specific heat of water is 4.184, and the units are joules, those are energy units, right? Divided by grams, which are mass units, divided by degrees C, which are temperature units, okay? That value, 4.184, is used in a lot of different problems. So you don't need to memorize the table, but that one you might want to know, 4.184 joules per gram degree C. Just so you know, it can be in different units as well. So it could be in 4,184 joules per kilogram degrees C. So a kilogram is 1,000 grams. So it's 1,000 times as large, 4,184 joules per kilogram degrees C. Okay, so those are different units. Now, let's talk a little bit about how this is used. We're going to start by looking at what's called the constant pressure calorimeter. Okay, so the picture here is, let's make it a little bit bigger here just so you can see it. The picture here shows a constant pressure calorimeter. At the top is just a glass thermometer filled with, it's red, so it's alcohol. Mercury are the old thermometers, that would be a metallic color, but it's red, so it's an alcohol. And it's calibrated with different temperature gradations. There is, it's pretty primitive, right? 2 styrofoam cups, one stacked inside the other, with a little cork top, and the thermometer sticks through a hole in the cork, and then there's another tiny little hole where someone's taken a paper clip and bent it so that they can stir the liquid that's on the inside, and then there's a reaction mixture. Okay, now this is a very common type of experiment, and the idea is essentially that what would happen is you would have a reaction taking place inside this calorimeter. And so, for example, I'm just going to make a really simple reaction. Suppose it's HCl dissolved in water plus sodium hydroxide dissolved in water. And they react to form H2O and NaCl. Remember from chapter 4, acid-base reaction, you get water and a salt. Here's that example. It turns out this reaction is exothermic, so heat will get released as the reaction occurs into the water. And then the water will get hotter, and you measure the temperature of the water using the thermometer. The reason the stir is in there is just so that you can equilibrate the heat transfer, just make the heat not get collected in one area but transfer more quickly throughout the solution. And then it's insulated to make sure that heat doesn't escape too quickly, okay? So in this case, what we would do is we would calculate the heat that's warming up the water. The heat is coming from the reaction, it's going into the water, and so the heat transferred into the water would be the specific heat of water times the mass of the water times the change in temperature of the water. Okay? So that's how much heat went into the water. How much heat came out of the reaction? Well, the heat of the reaction, the heat is coming from the reaction and going into the water. So that means any heat that the water gets came from the reaction. So it would just be the negative of the heat of the water. So in practice, what you do is you calculate this. You measure and calculate. And then from that, now you know this one right here, you can find the heat of reaction, Q of the reaction. Since this is being done at constant pressure, let's bring it back to the previous section. At constant pressure, QP is equal to delta H. So in other words, we can get the enthalpy change for the reaction. I'll put Rxn down here. Enthalpy change, delta H, of the reaction, Rxn, is equal to that Q sub P, which is Q of the reaction, okay? And that's what we get from just measuring the change in temperature of the water, okay? That's called constant pressure calorimetry, and it is a very common technique for measuring how much heat is released in a chemical reaction, okay? Now let me show you a few values. Let me come back up here. A few values of chemical reactions in their delta H's. So this is from table 5.3. Typical reactions. Rxn for reactions and physical processes. So energy is exchanged during certain processes. So here's one, the one I just showed you. This is called heat of neutralization. If you remember back from chapter 4, neutralization, acid neutralizing a base. An example of that is HCl plus NaOH. That's the one we just did, right? H2O, NaCl. And then put a little symbol here, delta H. The heat of reaction for that process is negative 56.2 kilojoules per mole. In other words, if you take a mole of HCl, a mole of NaOH, and react them, the amount of enthalpy change associated with that reaction is 56.2 kilojoules. And the fact that it's negative, what does that remember? What does that mean? Remember what negative means? That means it's exothermic. So that means that it will release the energy to the surroundings, meaning the water will get hotter. And exothermic reaction in water makes the water hotter because it's releasing energy to the water. Endothermic, which is positive, would be the opposite. The water would actually get colder. You would see it get colder. It could even freeze the water if it's endothermic enough because the water is transferring the energy to the reaction. Isn't that interesting? Another one is called heat of fusion. Now, this is not a chemical reaction. This is a physical process. And an example of that for water is this. Melting water, so turning solid water, ice cube, right, into liquid water is +6, let me put delta H here, plus 6.01 kilojoules per mole. So in other words, if you take a mole of ice cube, a mole of water in the form of ice cubes, and you melt them, the amount of energy it takes to melt an ice cube, if it has 1 mole, which is 18 grams, it would be 6 kilojoules per mole. So it's an endothermic process, which means that the surroundings would give the energy for that to occur. Okay, it's an endothermic process. Another example, heat of vaporization. This is an important value for anybody who's a chemical engineer. So H2O liquid being converted into H2O gas. Okay, so we're going to call that delta H. And that one is 40.0 kilojoules per mole. Sorry, let's do it at 100 degrees C, just so that it's more practical. We don't usually boil water at 25 degrees C. So at 100 degrees C, it's 40, I'm sorry, I'm not writing this very well, 40.79 kilojoules per mole. So in other words, it takes almost 41 kilojoules to boil liquid water at its boiling point at 100 degrees C. Okay, almost 41 kilojoules, and so that's the heat of vaporization. Okay. Now, the last issue that I want to talk about is what's called constant volume calorimetry. And so here is a picture of a calorimeter, but this one looks quite a bit different than the one we looked at before. Remember, this is the constant pressure calorimeter. Very simple device. You can make this at home really easily. All you need are styrofoam cups, a thermometer, and a paper clip. And you've got it. You've got yourself a constant pressure calorimeter. Okay? You could do a reaction at home. You just take some vinegar and some baking soda, put it in there, measure the temperature change, and you could do all kinds of experiments that way. Now, the constant volume calorimeter is a little more complicated. So let me go over this picture here. It looks more complicated, right? So here what we do is we have a stainless steel device called a bomb. And in this case, the bomb, they call it a bomb because there's going to be a detonation inside of this. So the bomb is made out of steel, and it usually has a screw cap on top so that you make a nice seal. And then it usually has like a tube that allows oxygen flow into it. Okay, so it can handle high pressure oxygen. Typically the pressure of oxygen might be 10 or even 15 atmospheres of O2. We would purge out any air that's in there to get out of the nitrogen. Okay, and then there's usually a little cup, a little sample cup, just so that if the sample falls, it falls into that. Okay, so this thing is filled with oxygen at high pressure. And then it also has a little wire. There's an ignition wire at the top. You see that there at the top? It says ignition wire. That ignition wire goes all the way down to the cup. Okay, connects into there. So that's your wire. And then that connects in usually to some sort of power supply. Could be a battery. Could be even just 110 right out of the wall. Some sort of power supply, electrical. And then there's a sample in that cup. So the sample, usually the way it's done, out here, I'll draw it over here, is you turn the sample into like a little pellet. You press it into a pellet, and when you press into the pellet, you kind of carefully put the wire through it. You feed the wire through. If it's a liquid, then you just got to pour the liquid in the cup and stick the wire into the liquid in the cup, okay? But typically, if it's a solid, you press it into a pellet, okay? Then essentially what happens is combustion. So what you do is you turn on the power supply, a voltage goes through the wire, and that voltage going through the wire will just essentially, just like a spark plug, it'll ignite the pellet. The oxygen will combust the pellet. So the pellet, I mean, you're not going to do this with, let's see, what wouldn't you do it with? You wouldn't do it with a piece, well, I guess you could even do it with a piece of aluminum. Aluminum can combust at a high enough temperature. Typically, these are done with organic materials. So, for example, a famous experiment is where you take aspirin. So you take aspirin, which is a hydrocarbon. It has carbon, hydrogen, and oxygen. React that with the high-pressure oxygen gas. You get CO2, and then you get water, right? And here's what happens. If this is an exothermic reaction, if it's negative, right, delta H is negative, then what will happen is it will release heat into the oxygen that hasn't burned, and then that bomb is inside a water bath. There's a big water bath in here. So this is water. And that's where the thermometer is. The thermometer is in the water. So heat flows out of the bomb into the water. The water gets hot. Okay? So there you go. You're doing that same thing we talked about in a little bit early in our discussion here. You're essentially saying, look, Q equals C delta T, the heat capacity of the calorimeter times the change in temperature. Okay? So this is essentially constant volume, not constant pressure, but constant volume. So what did we say about constant volume back when we talked about enthalpy? We said that if we're at constant volume, the amount of heat is equal to the change in internal energy, delta U. Right? So if that's the case, then that allows us to find the change in internal energy from this particular reaction. Okay, so that's called a constant volume calorimeter. Okay, so there's a nice little introduction. Oh, I should point out that these are what's used to find the calorie intake or the calorie content of certain foods. So for example, let me just throw this out here. See if I can fit this over here. I'll just come up here to another page. You may have heard that carbohydrates right, which would be like, sugars or vegetables, those sorts of things. Carbohydrates have 4 calories per gram. So a gram of carbohydrates has 4 calories. You may have heard that proteins are the same thing. 4 calories per gram. And you may have heard that fats have more energy, 9 calories per gram. And then alcohols are 7 calories per gram. Of course, water doesn't have any, right? The reason for that is that our metabolism, the way we metabolize foods, we can really only get energy out of these materials. These are the 4 materials we can get energy out of, as far as I know. And the amount of energy we get is essentially combustion. Essentially, we combust internally. We combust these materials to get energy out of them. Okay? So essentially, you take your carbohydrates, you breathe in oxygen, you combust the carbohydrates into carbon dioxide and water, right? You pee the water out and you breathe out the carbon dioxide, but you get energy out of that. And so these are the energy contents of those. So how do we know what those values are? We know them through constant volume calorimetry. What they do is you dry it out, you make sure there's no water in it, but you take a piece of something that's maybe protein, and you do the combustion, you measure what the heat content is, how much heat it releases in the reaction, and then you make that per gram. And you do the same thing with carbohydrates. You do the same thing with fats, okay? So that's how you tell. Now, a little bit about units. When we say that carbs have 4 calories, it's actually kilocalories. Food calories are what we call kilocalories. Okay, food calories is a kilocalorie. So 1 kilocalorie is 1,000 calories. So if you eat a piece of food that has, let's say, 10 grams of carbohydrates, that would be 10 grams. So 4 times 10, 40 kilocalories of energy in that. And there is a conversion from calories to joules. So 1 kilocalorie is equal to 1 kilojoule. I'm sorry, what did I just say? I don't know why I said that. One kilocalorie is equal to 4.184 kilojoules. Or 1 kilocalorie is equal to 4,184 joules, right? So a kilojoule is 1,000 joules. So 1 kilocalorie is 4,184 joules, okay? So let's say you eat, a bag of chips, and that chips has, 20 grams of fat and 10 grams of carbs. I don't think chips have much in the way of proteins, right? Or alcohols for that matter. So what you could do if you wanted to calculate how many calories that would be, you would take 20 grams of fat times 9, 20 grams of fat times 9 calories, kilocalories per gram. And that would be 180 kilocalories. And then it has 10 grams of carbs, so that would be times 4 kilocalories per gram. And there you'd have your 40 kilocalories of energy. Add those up, and you would have 220 kilocalories. So on the label, it might say calorie, but it's really kilocalories. I just don't bother to put the kilo in there. And if you wanted to convert that to joules, that'd be pretty simple, right? Because you know that 1 kilocalorie is 4,184 joules, so you could use that to do a conversion into joules, okay? So there you go. There's an intro into calorimetry.